Okay, so today we're going to have our last lecture on visualization, which will be on the three-dimensional visualization using Python. And we'll be looking at three-dimensional lines, surfaces, and also vectors. Well, vectors is not necessarily three-dimensional. So in last lecture, we learned an important concept about how to generate a two-dimensional mesh, use the mesh grid function. And we learned how to generate two-dimensional pseudo-color plots using the p-color function, and how to generate contour plots and contours with filled colors. And also we learned another set of Python tricks trying to plot all the data together on maps using the base map module. So in this lecture, you will learn how to plot data in polar coordinates. These will be 2D. And we will start to look at 3D line plots and 3D surface plots with colors and shapes. And also we will look at vector plots. And I'll save the streamline plots as a part of the practice in the practice file. So if you look at these figures, right, these are figures from my research work. And you can see that these are very colorful, fancy structures of different parts of the geospace and the heliosphere. So if you look at this, is basically the dynamics variation of the air density of the thermosphere, which is at 400 kilometers altitude. And you can see that the Earth is rotating, and you kind of see this three-dimensional shape and surface of the Earth colored by the air density down here. Right, in case it's very dynamic. And if you look at the other one, and this is also a three-dimensional cuts from a in the meridional plane, equatorial plane, and you can see the solar winds pinching, squeezing the Earth magnetic field, and you see these are field lines. So these are actually colors with line plots with three-dimensional line colors. Right, so this is actually a CME, which is coronal mass ejection. That's how the solar storm is coming from. So that's the surface, not the surface. It's actually above the surface of the sun. And you can see these are actually the high-speed solar wind coming out from the sun. And these fluffy structures. These are the structures of the magnetic field lines of the sun. So these are three-dimensional surface plots, color plots, plus line plots. So that's why when you do visualization for scientific data, you will need three-dimensional plots with colors and also plot some lines. Here, there's streamlines or magnetic field lines. All right, so types of three-dimensional plots usually have 3D lines, as you've seen from those field lines or streamlines, and surfaces, and that's either the Earth surface or the surface with different heights, and also three-dimensional vectors and streamlines, and we'll see how that go. So before we dive into the 3D line plots, and let's first learn how to make 2D line plots in polar coordinates. So you're already familiar with 2D line plots in Cartesian geometry, because that's plot xy, right? So in polar geometry, things are slightly different, because in Cartesian, you have the x dimension and y dimension, and use two numbers to do that, which is x and y. So in the Cartesian geometry, just do p color a plot xy, p color xy, a contour xy, etc. Right? So in the polar geometry, you don't describe the points x and y. You are actually using the other two parameters called r, which is the distance from the origin, and also the theta with the the x-axis here. So r theta. So if we know a function, a relationship between r and theta, or for example, r is a function of theta. So how do we generate a plot in a geometry like this? So you can do that with Python. So first I want to remind you is that the relationship between a polar coordinate and a Cartesian coordinate. So for example, if I have a point in the Cartesian coordinate, it's x and y, while in the polar coordinates, it's r and theta. So r is the distance from the origin, and theta is the angle between the red line and the positive x-axis. So you can see that the relationship between x, y, and r theta is x equals to r cosine theta. This is x. And y equals to r sine theta. That's y. And x squared plus y squared equals r squared, y divided by x tangent theta. right? So once, for example, this is important when you do gridding. For example, if you generate a mesh grid in the r and theta coordinates, and you can use this relationship between x and y to convert r and theta to x and y, and then use all the plotting functions that we've learned to do polar plots, right? So three-dimensional, it's the same thing, right? Because now we have another dimension, which is phi, is the azimuthal direction. So you can see here is that r theta is basically the latitude or the co-latitude, and phi is the longitude, right? So the relationship between r theta and phi to xyz is described by this set of equations, and you will try to use that. And you can see that theta here is basically the co-latitude, or close to latitude, which is from minus pi over 2 to pi over 2. And phi is the longitudinal direction, right? So for example, if you generating a two-dimensional grid of longitude and latitude, and you can use this three equations to convert the longitude and latitude to XYZ, right? For example, because R is known for the Earth, it's the surface of the Earth, right? You can use it as one. Right. So let's make an ellipse first. So ellipse functions have different forms. For example, in the polar geometry, and it goes like r equals to ra divided by 1 plus e times cosine theta. So ra is semi-major axis, and e is the eccentricity, right? Theta's form is the variable, is the angle from 0 to 2 pi. So if we say, let's use a Python code to draw an ellipse with ra equals to 0.0 and eccentricity equals 0.3. So eccentricity is basically how elongated of the ellipse is, right? You can see that if eccentricity is 0, then r equals to ra, which is constant, so that's a circle, right? So you can see that the curve we do is that we're gonna plot r as a function of theta. So r as a function of theta. So first let's generate a grid of theta, which displays between 0 and 2 pi using 100 points, right? So it's a length space function, and these are parameters. Now we write down the ellipse equation, r equals to ra divided by 1 plus e times cosine theta. And then we plot, instead of using plot, now we're using a function called polar, theta and r. So if you do that, Python knows that you're plotting the relationship between theta and r. Basically, you're generating r as a function of theta, right? So then it's gonna generating a circle like this, ellipse like this. You can see this is basically the results. So the syntax of generating a polar plot using the polar equation, which basically goes plt.polar theta and r. So r is a function of theta, and it's defined, for example, for ellipse, it's defined by this equation. All right, so let's try something more complicated. And instead of generating just a boring ellipse, let's plot to the orbits of all the solar planets with data. And then we're gonna use pandas, for loop, and PLT. All right, so first of all, let's load the data. So the data here is called planetary orbital.excel. It's an Excel file, and I'm setting the index column to be the first column. If you still remember, index call equals 0, and then print out to the head function. And you can see that this is the data that I have. So that's my index. These are planet names. And I have the semi-major axis, which is RA, eccentricity, which is E, and then these orbital periodicity, mass and moons, and we're not going to use those. So we're going to only use these two, right? So if you look at, this new trick of how to going through each rows of pandas, some of you may have already tried this in previous homeworks and exercise. So what I did here is because I'm going to loop through all the rows of this data frame, df here, right? So the syntax goes row in df.head dot iter tuples, so iterating tuples. So what this does is this df, so I'm only plotting the first 5 planets, df.head, and dot iter tuples, it's taking a row of the pandas data frame and give you access based on those column names, right? So you can see that now eccentricity is basically row dot eccentricity, right? If you look at this. So starting from the first row, so row is going to be this data structure with these things and that index here. So you can see that RA is row dot semi-major axis. Now I'm generating R equals to RA divided by 1 plus e times cosine theta. Remember that theta is the linear space between 0 and 2 pi with 100 data points. And now I do PLT dot polar plot relationship between theta and R, and I'm giving the label, which is the name of the index, right? And I put on the legend. So the row does this, for loop does is that it's gonna loop over all the rows of the data and give this to be RA, give this to be E, and generating a polar equation for ellipse, and then use the polar function to plot it, and go through all the rows in the df dot head. Right, so if you done that, and you can see that I got 5 orbits from Mercury to Venus to Earth. Earth is exactly at 1, that's at 1 AU, and that's Mars, and that's Jupiter. Right, so this is how we do that. So that's how you learned in this small piece of code. We basically reviewed pandas data frames and how to loop over data frames and using for loops and how to generate ellipse functions and using the polar function to plot those orbits. All right, so now let's try to visualize orbits in 3D figure. So in the 3D figure, we're going to use another couple of tools called mplot3D. So that's matplotlib 3D plots. And we also use another function called axis3D. That's actually another library. So you can see that the syntax will go fig equals to plt.figure. So we're generating a figure with the size, and we're generating axis, and projection will be 3D. So after you did this, the plt.axis function creates a 3D axis, looks like an empty box. And then it has the X and Y and Z extensions for your 3D dimensional visualizations. So based on this X object, and then you can plot your 3-dimensional structures in this 3-dimensional box. Right. So let's try to visualize the orbits in 3D by adding a Z extension. Right. So now what happens here is that it's the same code loading the orbit dynamics. So I've already created the 3D box for my figure using the fig and X, which is figure and axis functions. So now I'm looping through all the rows using the iter-tuple method of data frames. And then you can see that I get these parameters and I'm generating the polar function of all the orbits in the polar coordinates, right? So since 3-dimensional plots, we don't have any polar plots, you don't have the 3rd dimension, right? So we need a Z. In this case, what I did is that now I'm converting R and theta to X, Y, and Z. Right? So X, Y are very straightforward. It's R cosine theta and Y equals to R sine theta. And Z, it has the same size of X, but it's all 0 because my assumption is that all the solar planets orbiting in the plane with Z equals to 0. Right? So now we can use a new function called plot3D, X, Y, and Z, and put in a label and length width. So in this case, the orbits of all the planets will be showing in the 3-dimensional box, if you still remember in the previous slides, and you can see how they look like. So this is basically a new function. It's called plot3D, does the job. You need X and Y and Z location of those curves, right? So that's a 3-dimensional orbits. And you can see that now I have a Z extension. Instead of looking down, I'm actually looking from the sides, right? So you can see these orbits of these planets, and you can see that, Jupiter is actually really far away from the Earth. So the syntax here is plot 3D and X, Y, and Z. So X, Y, and Z are all Cartesian locations for a 3D line. Right? If you put in R theta, it's not going to work because R theta only works for polar geometry. Right? So a couple of things to understand is pandas and how to loop over pandas rows using a column, using the column, the row in iteration method. and also how to generating the ellipse and converting the polar coordinates to Cartesian coordinates and then generating plot. Right? So it's a small piece of code, but has lots of techniques involved. Right, so let's try to visualize the trajectory of Voyager 2, which is such a miracle. So the Voyager 2 mission is still, I think it's probably the most prominent human mission into the space heliosphere, which was done 30, 40 years ago, and it's still flying, it's still transmitting data these days, which is amazing. So what happened here is that our astrophysicist orbital dynamics research figured that there's once in a thousands years of time that you can have the Mars, Jupiter, Saturn, Uranus, Neptune, all aligned more or less in the same on the same side of the solar eclipse plane, and then you can launch a spacecraft from the Earth and through the acceleration using the gravity slingshot method. So the Voyager 2 launched on the Earth and went through Mars and went through Jupiter and gets accelerated and get the velocity of Jupiter, and then go all the way to Saturn and then gets accelerated by the gravitational field of Saturn and accelerated to the speed of Saturn and then accelerate at Uranus and accelerate at Neptune and then go all the way leave the solar system. So that's called the miracle path. And these data are open, and you can download the data and visualize these trajectories and see how it works. So here's the visualization code to plot the Voyager 2. Right. So the first piece of code we've already talked about, this is basically plotting three-dimensional plots of the orbits of all the planets. And then the other one we need is another data file, which is the trajectory of Voyager 2. So it's VY2 traject in one-dimensional resolution and ask.txt. Right? So in this file, and then the delimiter is basically space. So if you still remember what delimiter is, so we need to figure out how the data points are separated. So here it's space, it's /s plus. And then if you look at the data, and it'll be time, year, day, and also distance. This is basically r in the polar geometry. And this is basically theta, which is this longitude in the polar geometry in degrees. So what we need to do here is that we need to get this column and that r column, theta column, and convert that to x and y and z, right? So what we did here is, that x equals to r times cosine theta. If you still remember, that's r and that's theta. Sec ln, that's theta, right? Y equals to r times sine theta, and z is 0 because it's almost in the elliptical plane, right? So if we do this and we use plot 3D XYZ and color, and then you can label it Voyager 2, and then we generate a plot like this. I mean, it's 3D plots, but is it nice? Which one is compared to the previous page of the 2D one? Which one's better? Well, it's 3D has more information, but more information does not necessarily mean it's always nicer to look at. All right. Okay, so now let's go to the next topic, which is 3D surface plots. So remember that in 2D color plots, you're using p-color. So x and y are the grid size of the grid, two-dimensional grids, and z is basically data, right? The color, the figure is colored based on z. So if you interpret z as the height of your grid points, and then you can actually mesh the points based on the location x, y, and z, and that's basically a 3D surface plot. And we have functions to do that. Right? So recall there's 2D color plots, and we generate this function x, y. So x, y are 1D arrays, and we use mesh grid to get capital X, capital Y. So these are 2D arrays based on these 1D mesh. And z is basically sine x times cosine pi y. So right now we did p color x, y, and z, and use a red-blue color bar. And this was what we got last time, right? So now this time, let's try a new trick, which let's see Z is going to be the height of all the points X and Y. Right, so you do the same thing. You're generating 2D mesh grids. It's the same. So I created a 3D axis, which is the 3D figure. And now I plot a surface, which is called surf, equals to x dot. The function now is called plot surface. Right? So plot surface will be x location, y location. Now z is basically the height of all those corresponding x and y locations. And I give a color bar, and that's the view initiation. So that's a viewpoint angle. We will talk about that later. So if you run this code and you get a surface like this, right? So instead of giving you just the color, and you actually get a different z locations based on the value of z you use in the plot surface function, which is pretty straightforward. Right. So this is the function does the job. So the view angle is actually quite straightforward to do, is that you have two inputs. One is elevation. So that's how high you're looking at. So for example, this is your eye, you're looking down the figure this way. So the view angle equals 0, you're looking from the sides, right? So the view angle, the elevation equals 90, and you're looking from the top, right? Azimuthal is basically rotating in this direction. So let's take a look at, for example, I'm looking from elevation 45 degrees, azimuthal 45 degrees. So I'm right looking at the diagonal of this plot in this way, right? Looking at 45 degrees. So if I do 90 degrees and 90 degrees, so 90 degrees elevation, look at this plot, your eye will be moved to here. So you're looking down, right? So the last one, if you look at elevation 0 degrees, your eye will be looking from the XY plane down here. So you're looking at the sides, and you see these, up and downs in the surface in the shape of the plot. Right? So this is how you control the view angle to control the size and the look of your figure. Right. So let's take a look at an example of 3D surface plots to look at a plot gravity anomalies. Right. So here are descriptions, lots of descriptions of the gravity. So the point here is that if you don't understand the details, doesn't matter. The point here is that the formula for gravitational attraction of a sphere buried down the surface is described by this equation. So the physical picture here is this way. So that's the surface, ground surface, right? So this R is a sphere with density, density differences of delta rho buried down with the height, depth of z down here, right? So g here is a function, basically g is the gravity that's caused by this object down there. And g is a function of r, which is the size of the object. G is the gravitational constant. And delta rho is the density difference between the sphere and the surrounding area. And more important, it's a function of h and z. So h is the distance from z to the center here, and z is the depth. Right? So basically, that's the function we're going to use. So for example, the idea here is that if we given all the parameters, including g, delta rho, r, and what's the shape of the gravity as a function distribution in 3D plot. Right? So first, let's create a gravity function based on this equation. And we're using the lambda function. So it has 5 parameters, g, r, d rho, h, z. So that's the same equation as this one. Right? So now let's create a mesh to visualize the gravity distribution in a 2D surface. And you can see that we're generating x-axis from -6 to 6 with delta x 0.1. So I'm now using the A-range function. So y equals to also -x, 6 to 6, and point separated by 0.1. So x and y, capital X, capital Y, that's mesh grid. That's a 2-dimensional mesh for plotting this function. Right. So you know that horizontal distance is basically a square root of x squared plus y squared. So in this case, h equals to square root of x squared plus y squared. So given the z and given g, r, and d rho, and then we can get the gravity as a function of h, which is also a function of capital X and capital Y. So remember that capital X, capital Y, these are 2-dimensional arrays of the mesh for the x location and y location. When you've done that, then gravity is also a two-dimensional array with all the gravity at the x and y locations. Then we can use a plot to do that. If you still remember that the contour F last time we did, so if we just do the x and y with G, and what you get here is basically a two-dimensional contour. I'm using contour F. I'm filling the contour with 20 levels in this way, right? So in the 3D plot, if we use the plot surface function, and we generating the plot with axis 3D. So AX is going to be my axis object. It's using generated by axis 3D in that figure. So surf is going to be my gravity surface. So I'm using a function called plot surface x and y, and g is the gravity on each x and y point, because g is a function of x and y. Right? So if you do that, and you get a surface like this. So which is quite straightforward to see because the object is buried at 0, z equals to x, y equals 0, z equals -3. So you can see that at the 0 point origin, and you can see you have a peak gravity around 12 milligauss or microgauss, right, in this way. So that's that's a very straightforward way to generate the three-dimensional surface. Remember that you use the plot surface function to do it, right? So the last part, and we'll be looking at the vector plots in Python. So the vector plots in Python are done using the quiver function. So for example, gravity, we know that gravity is a vector. So it does not only have a magnitude, it also has a direction, right? So for the direction, to describe a direction, you need two components. One is the component along the x direction, and the other component is around the y direction, if we only look at two-dimensional vectors. Right? So in this way, so we're doing the same thing here. So I'm generating a mesh, and I generated the gravity function here, g, and g is basically gravity on the same mesh x and y. So in this case, I'm gonna generating the vectors based on another equation, basically. So the x component, which is called u, and that's minus x times g. So minus x is the 2D mesh of the x locations, and g is the gravity on all those 2D locations. And v is the y component. It's minus y times g in this way, right? So now I have x, y location of my these should be capital X and capital Y. So check the Jupyter Notebook file to make sure it's correct. So X and Y, and using U and V in this way. So U is X component, V is Y components, and the quiver function will give you all the locations, the directions of the gravity. So you can see that everything's pointed towards the center. And as you go further in, the vectors actually increases. And then as you go further out, and the vectors actually decreases, right? So the gravity changes with both the magnitude and the direction changes with location. And you can see that's basically how you generate a vector plot using a quiver function. So if you want more about the quiver function, and you can look at more details on these matplotlib page about three-dimensional plots. So 3D plots are useful, but they're still, in lots of stuff they're still in progress. And you can use other libraries like the MLab or MayAVI, all these ones, but these are more advanced topics, and when you need them, and you can just go trying to search online to find the documentation and make those plots. And there's lots of things that you can do with the 3D plots, but most of the projects are, because they're open source projects, so maintenance is a problem. So a version of the code may not work with the newer version of Python. So that's unfortunate, but people are solving those problems. All right, so this is an example of one of the figures from my research, and you can see that this is an animation of a geomagnetic storm. So if I let it go, and you can see that the points in here is that not trying, don't just ignore the details. So the idea here is that you can see, I have one-dimensional line plots showing the measured, air density and the activity index. And then you have 2D plots of, the ionospheric convection and the heating, and also 2D cut plots of the plasma density of the geospace, right? So here's the sun, that's the solar wind, and you have arrows to showing the direction of the solar wind and the speed of the solar wind. And also now here you have the three-dimensional surface showing the mass density of the thermosphere at 400 kilometers. And then you also have a one little circle circling around, that's the CHAMP satellite. Right? So this is a very complicated plot, but this is a nice example of showing you that when you do research and you can generating very complicated plots like this and using the 1D to 3D techniques we've learned to generate plots. All right, so here are more examples that you can use if you're interested in your future, research or future work, and you can try to use all these complicated, three-dimensional plots, and you can find all these examples about the Access 3D examples in matplotlib.org. That's the official documentation of Matplotlib. All right, so now let's try to do some exercise with the 2D and three-dimensional plots.